All right, so this is example 6.5. Again, I made a couple little changes here just in the estimate here just to kind of, so I can explain this in the video a little bit better, I think, than the notes. Remember, this is the case where the bar has an initial temperature distribution. The ends of the bar are not insulated. And the bar is basically at time zero placed into a room with regulated room temperature that stays constant. So we don't really have a boundary condition as in the previous two models. Remember, in the previous two models, we either said the heat could not flow in or out of the bar because of insulation, or we said it could flow in or out, but the temperatures at the endpoints would be fixed, not allowed to change. But in this case, we're not really saying that. We're saying that the steady state distribution of the bar will equal that of the room temperature. So eventually, over a long enough period of time, the temperature across the bar should match the room temperature. So again, let's go back to the summary in the theorem that kind of summarizes all this information for this case. Remember our assumptions where f is continuous and differentiable for x between 0 and L, and it has a square integral derivative. Those are just the theoretical assumptions and realistic assumptions, really, that will make sure that our series that we have for our solution U will actually converge uniformly. And then we had this weird construction that we did. We broke our function f into two pieces. They were called f subscript s and f subscript c. And the idea was we had to split f into two functions. And one of the functions we would use to define the sine part of this solution. And the other part of f would be used to define the cosine part, which also has the constant term r as our room temperature. So as time goes on, this whole series will converge to 0 and we'll be left with the room temperature because of the exponential decay factor in the terms of the sum. But in order to do that, we made an observation as we went through. How did we get that to happen? We had this parameter lambda which was defining those functions for us. So for example, in the b sub n, what we're actually using is computing the Fourier series of the odd extension of this function highlighted in blue. And this is what we called f subscript s of x. So this is the part of f which we're using to encode all the extra energy in the bar that has to eventually flow out into the room and then be dissipated so that the bar can reach its room temperature. The other part, which we call f subscript c of x, was basically just f minus f sub s of x. That's all this is. It's just f of x minus f sub s of x. So when you add those two functions together, you do get f. This is defining the cosine coefficients. And so what it's actually doing is this is encoding the room temperature that exists in the bar so that as time goes on, this portion of the solution maintains that room temperature in the bar and doesn't allow anything else to flow in or out. But both of these parts are working at the same time together, so it really just looks like the extra temperature is leaving. If the bar is cooling, for example, as in this example, over time till we get to the steady state constant room temperature. So we introduced this parameter lambda to tell us how to split the function f. No matter what we choose for this lambda, these two functions fs and fc will add up to f. So this is a free parameter. And what we had to realize is that when we computed the coefficient a sub 0 of this function fc, we just had to set that equal to r and then solve for the parameter lambda so that we could choose lambda to make sure that in our solution we can put r as the constant term. So lambda ended up being this formula here. It's just the integral of f minus L times r, all divided by the integral of this thing which is without a lambda, but it's basically fs of x, but the lambda's been canceled out algebraically. Well, because we solved for lambda here. So basically, once you're given f, and you're given r, and you're given l, and you're given little number c, you can compute this lambda as long as you don't divide by 0. And that's where that condition comes from, that we assume that this integral is not 0. Again, I give a remark later that if you were in a case where this were 0, we could just use a different way of splitting. I mean, for example, this power of 2 is nothing special. We could have used a power of 3 or 4 or 1 if we really wanted to. So if one power here doesn't work, gives you an integral 0, try another power, and then that would be non-zero. And then you could use the same formula. You just have to use that power throughout. That's one way of doing it, but there are lots of ways of doing this. So once we're given all the information, we can compute this lambda, which allows us to construct our functions f sub c and f sub s. And then once we have those functions defined, we can actually get formulas for a sub n and b sub n, and then we just have our solution here, where r is the room temperature, and that's a steady state temperature. All right, so back to our example. We do all that, computed lambda, given all the given information, to define our functions so that we can compute the coefficients. And we did, and again, because of the splitting, these coefficients can look quite nasty, but in the end, they're the same thing we've seen in other examples. It's really just about powers of n for this example as well. So again, I'm not going to go into the details of this one because the numbers are very big. But if you do a rough estimate of this numerator, all you have to look at is just take the absolute value of every term, so you have a sum, no minus signs anywhere. And then you just look at the terms. Some of the terms have an n to the 4th power, some of the terms have an n squared power, and some of them are just constant terms. So as another way of getting an upper estimate, replace all the terms you have by making sure they all have n to the 4th power. That will make the constant terms bigger, and it'll make the n squared terms bigger, so it's still a good upper estimate. It's just quite a big upper estimate. But in the end, that allows us to algebraically simplify this to some constant over n squared. And the bn is similar, but not as complicated. And you could actually estimate this one better with a constant over n cubed. Now, these two constants are different. But what that means is the a sub n's are really decaying to 0 slower. So those are the ones we want to use. So what we could do is do an even more of an estimate here and just say replace n cubed by n squared, and we definitely got a bigger value here. So then we could basically take the two constants from these two estimates over n squared and add them together, and that would be our capital C from our formula for our error for determining how big n has to be, capital N has to be. But anyway, let's kind of skip through that for this. This is just, you've seen enough of that, you've done enough of that for other examples. It's the same thing. So here's the temperature, first like couple intervals of time here where this is changing. You can see the endpoints are initially are converging quickly to the room temperature, and the middle of the bar is not converging as quickly because it's insulated. It's further away from those exposed ends. So it takes a little longer for the middle of the bar to cool down. So let's look at the actual what we have here. So again, just defining everything again, defining our given information, computing what that lambda is, and for Maple I'm using p instead of lambda because lambda is actually, the word lambda is actually reserved in Maple as some variable, so just using p instead. And then I'm defining n equal 25. Again, just because it's big enough to give us a reasonable visualization that does look pretty accurate. It's much smaller than what we get from our rough estimate. But remember, a rough estimate is rough, so it usually gives us a value of n that's way bigger than it really needs to be. So I just did some trial and error here and this looked like it would be reasonable. It doesn't take us too long to process. So then again, all I'm doing is once I have that p, which is really lambda we were talking about before, I define my two functions fs and fc to be two things that add up to f. Again, I'm going to show you the formulas that Maple spits out, which are the ones in the notes. And then I'll actually have Maple compute the numerical values of those for all the 25 coefficients we need. And then we just define the function u, which is really our approximating function u sub n. And then we'll animate it. And I've already done this to save some time because it does take a little bit of processing time. You can see the formulas here are the same ones. The terms may be organized a little bit differently, but they're the same as we have in the notes. And here is our animation, which I've already run through, so let me start it over. So there's our initial temperature distribution along the bar. So along the bar, length 4, the temperature at 2 is 2, 4 is 4, and any x is x. So I'm going to run through this first 20 seconds of this or so. And again, you see that the temperature at the endpoints go much more quickly in the beginning down towards the room temperature because those are the ends of the bar that are exposed to the room temperature. The middle of the bar is not exposed, so it takes longer for the energy to flow out of the ends of the bar. And you can see at 20 seconds, we still are not we're not really that close to the steady state, so it will take a little longer for that to happen. So just kind of run to the beginning of this again. You can see that initial quick change in the endpoint temperatures. And then much slower as time goes on. All right, so let's make some sense of how we split this function f. So what I have here are those two functions I used and multiplied by f. So this function here is really what I multiplied by f to get fs, and this function here is what I multiplied by f to get fc. So the red graph is what I multiplied to get fs, the blue is what I multiplied by f to get fc. And again, the point is these two functions add up to 1. So if you look at the heights of the graphs at any x value, they add up to 1. So here at the endpoint, you can see the blue graph is height 1, the red graph is height 0. So you add those together, you get 1. But that's true everywhere. So a better graph is to look at actually what happens when I graph fs, fc, and f all in the same graph. So this is not to scale. The vertical scale is different than the horizontal scale. So the green line is our function f of x equals x. And now we can see that the red is, this is our fs of x function that we use to define the sine part of the series. It has the key feature which allows us to do that, which I ask you about in another exercise. So we're basically using the odd extension of this red function to compute the b sub n's. And we're using the even extension of this blue graph to compute the a sub n's. So again, if you add the heights of the red and blue graph, what you get is the height of the green graph, f, because these two functions are just the two parts of f. So let's see how this changes as we change the problem and we change the room temperature. So we change the room temperature. Let's make it say 1 degree. And what that's going to do is that's going to make the room temperature closer to the average temperature along the bar in the first place. So there's not going to, what that means is there's not going to be as much energy loss throughout the bar over time. Again, this changes the coefficients because if you change r, you change lambda. You change lambda, you change what fs and fc are, so therefore you change the coefficients a sub n and b sub n. So here now, the height here at 1 is where we're going to see convergence to. So the left endpoint is going to go up, the right endpoint down. And we'll see stabilization towards a horizontal line at height 1. and again after about 20 seconds. In this case, it's a lot closer. And again, the reason is because the temperature of the room was not as extremely far away from the average temperature already in the bar. So now let's look at the difference. By changing the room temperature, what are we really saying? We're saying what we saw in this animation is that there's not as much energy that needs to flow out of the bar. So that means that the function fs is not going to be as important, or as a big part, as it was in the previous case. So if we look at these two pieces that should add up to 1 again, fs should be de-emphasized, the red should be de-emphasized, and the blue will be emphasized a little more. So you can see the blue graph now is higher, doesn't have negative values anymore. But again, these two graphs still add up to 1 at every x input. So now in this graph we'll see the red graph will be less important part, which will make the blue graph actually somewhat closer to f itself. So now you can see the red graph was de-emphasized. Now the blue graph is matching the initial distribution better. And we can actually see if we actually make the room temperature equal to the average temperature in our bar. Well, what is the average temperature in our bar? Well, our function's x from 0 to 4, so what would that be? I would have to have, I'd have to integrate x from 0 to 4. What's that going to be? So x squared over 2, so 16 over 2 minus 0, so it's 8. Make sure I'm doing that right. And then I have to divide by 4, so it should be, well, it should be right in the middle, it should be 2. So 2 is the average temperature of this initial temperature distribution. So if I make the room temperature match that, what we'll see is basically the function fs is 0. There's we don't need anything, really. Well, it's not going to be necessarily 0, but we'll see how that changes here. We still have to have heat flow in and out. Here's the animation. Now it's going. Oh, something's wrong here. What's it doing wrong? Oh, I put 0, not 0. I wanted 2. Sorry about that. I wanted 2 to be. Yeah, see, we can see what we have. The bn's are all 0. That's what I mentioned before. So the sine part of the series goes away. So all we really have is the cosine part of the series, because the average temperature in the bar is actually staying constant because the room temperature matches the average temperature in the bar. So there is heat flowing in and out in this example, I mean, in a realistic sense, but the mathematical model itself isn't actually showing really that. Well, let me correct myself. The model is correct. There is no flow because basically the energy inside the bar is staying in the bar. It's just redistributing itself because the room temperature outside isn't telling the energy that it has to leave. Now, in reality, there would be some energy transfer in the initial time, and that's the approximation of this model, because we can't physically make a room stay a constant temperature if the bar is going to have flow in and out of it. So there would be some little minimal flow, but it would be negligible in a sense. So in this case, again, we go back to this. There we go. The blue part is everything. So FC is F, and FS is just 0. So you'll just see that the graph of it, that's it. FC is the same as X, so it's actually underneath this, and FS is 0. So it's just off the graph.